I can cut it out. For now, all I gotta do is follow along. Yeah, maybe highlight would be a good idea. I guess I don't really need one. I got one on the screen. Oh, sorry, Okay, so, as I was saying earlier, I've sort of set you up pretty good for this. It's really not, it's just sort of a reverse way of thinking about force kind of problems. Okay? So this textbook here does a pretty nice job of sort of explaining things, so I like to use it as sort of an explanation from time to time. So let's talk about the net force. In the absence of force, objects stay at rest, and object continue motion. That's Newton's law, right? Mm-hmm. Objects in motion, or objects at rest, stay at rest. Objects in motion, stay in motion. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite force on opposite sides of an object at rest, it will remain at rest. And there's pictures over here that highlight this. The forces cancel each other out, and there is no net force. The combination of all forces acting on an object is called the net force. So this is kind of review, really, right? It's the net force that changes an object's state of motion. Figure 410, you know what, we don't even need to read through this. You guys know all this. Blah, blah, blah. Let's go right to this one here. Equilibrium, when the net force equals 0. Now this happens all the time. Like if all I'm doing is leaning against the counter here, I'm pushing with a certain amount of force, say, I don't know, maybe 100 newtons. The counter pushes on me, 100 newtons, right? Yep. Okay. Now, if I've only got 100 newtons of force on me, how come I'm not going accelerating that way?
Because,
you're putting the same amount down.
yeah, he's only putting...
Really?
Canceling.
Yeah, but the only force on me is the 100 newtons. Gravity down, true.
Because friction only uses what it needs to.
Is there friction on me?
Yes.
Between my feet and the floor, right? Like if I push really hard, I can slide backwards because I overcome friction, right? If I were on ice, if I was wearing like a curling shoe, I'd be like, kind of, right? Okay. So when you have no movement, when the forces are balanced, you are said to be at equilibrium. What forces act on your book while it's motionless on a table? Don't just say it's weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces a net force of 0. The other force is the support force of the table. Support force is often called the normal force, and you guys have been dealing with that since grade 11. As shown in figure 411, the table pushes up on the book with the force equal to the book's weight. When an object is at rest, with the net force on it being 0, we say the object is in a state of equilibrium. You are all in a state of equilibrium right now, right? Sure. Does the table really push up on the book? Yes, just as the spring pushes up in your hand when you compress it. You can feel the spring pushing back on your hand. Similarly, a book lying on a table compresses the atoms in the table. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be 0. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between the book and the table would feel itself squashed from both sides, top and bottom, as would you. When you hang from a rope, the atoms in the rope are not compressed. Instead, the atoms are stretched apart. A tension force is established in the rope. A rope under tension twangs, like a guitar string, if you pluck it. How much tension is in the rope when you hang from it? If you are in equilibrium, the tension must equal your own weight. The rope pulls you up, and the force of gravity pulls you down. So if the equal and opposite forces cancel each other out, you hang motionless. Now suppose you're hanging from a bar supported by 2 ropes, as in figure 412. Here you are right here. Neglecting the weight of the bar, the tension of each rope is 1/2 your weight. The total tension force acting upward, 1/2 your weight plus 1/2 your weight. So over here, let's say you have 500 newtons of weight force, then you'd have 250 there, 250 over there. Makes sense, right? Mm-hmm. When doing pull-ups using both arms, each arm supports 1/2 your weight. Have you ever tried pull-ups with just one arm? Yeah. Be virtually impossible. How come? Yeah, because you got to use both hands, right? Like you got to use both arm strength. Here, you're just using one arm strength. You have to do twice as much work with that one arm. A spring scale can be used to measure tension. When we weigh a bag of apples by suspending on a spring, the scale reading tells us the weight. Consider a 1 kilogram bag of 10 apples weighing 10 newtons. When suspended by a vertical spring, as shown on the left in figure 413, so down here, the scale reads 10 newtons. If instead we hang the 10 newton bag from a pair of vertical scales, as shown on the right, each scale reads 5 over here. See it? 5 and 5. How come?
Because it takes
Half and half, right? The total down, 10, has to equal the total up. And there's two of them doing the work. Yeah. Blah, blah, blah. That's what this is here, right? Okay. So, vector addition of forces. Now let's consider non-vertically oriented spring scales. In other words, they're not straight up and down. They are now sideways, like this. Okay. You lost? I haven't really given you anything sort of...
Yeah, I know, but it's...
All I'm talking about is when all the forces are balanced, that means the net force is
0.
and that means that the object's motion should remain the same. If it was at rest, it will stay at rest.
Oh, wait.
If the forces are balanced, right? If you've got more than one thing providing the force, like this, like if I've got 10 newtons down and I've got 2 spring scales holding it up, each one's going to be 5. That's all really I've said up to now. There's no real place to get lost in.
But what if like one spring is like sturdier than the other?
It'd still be 5 and 5. One might break sooner than the other.
Okay.
Yeah. Dawson? I think so. I think I'm recording.
On like,
Hello everyone out there in recorded land. Ty?
you're hanging by those 2 ropes.
Yeah.
You like are on like more on one side. It's like
Yeah, you get like, for example, I think there's a question coming up.
it wouldn't even it out.
There is one coming up here.
That was a dumb question.
Yeah, like when you step on a bathroom scale, the downward force applied by your feet and the upward force applied by the floor compress a calibrated spring. The compression of the spring gives you your weight. In effect, the scale measures the floor's support force. What will each scale read if you stand on 2 scales with your weight divided equally between them? All right, so I get on my scale. How much do I weigh today?
1,400.
825 newtons. Let's say 820. Let's say 800 for easy figuring. So if I've got 2 scales side by side, 400, 400, right? If I lean this way more, maybe 600, 200, right? Okay, so let's go back to this situation here. Let us now consider non-vertically oriented spring scales. In other words, they're at an angle. The tension is greater in a pair of non-vertical spring scales and depends on their angle from vertical. This more complicated situation is most easily understood using our good friend vectors. Recall our treatment of velocity vectors in Chapter 3. We'll now use the same vector addition techniques, i.e. components, with forces. Force, like velocity, has magnitude, direction, and is a vector quantity. So it says, look at the left of figure 414, right here. Notice that when the spring scales hang at 60 from vertical, so this angle right here, see it 60 degrees right there? Riley, you watching?
Yep.
60 degrees right there? The readings are 10 newtons each, double the tension of the vertically hanging scales. So now I've got, here, I've got 10 down, and now I've got 10 this way, and 10 that way. Well, what's going on here? I thought it was 5 and 5. It's not straight up and down. If it's straight up and down, it'd be 5 and 5, right? Okay, so there's this. Okay, this. Oopsie.
Oh, triangles. Oh.
Okay, let me redraw it. I'm gonna redraw this here. This is 10 here in blue. We have components. We have the vertical component up, and we have the horizontal component sideways. So if this is T1, tension 1, then I would call this one T1Y. Then this one would be T1X. Would the other tension have a Y?
Yeah.
It would. And those vertical components would have to
Equals it 5.
equal
Like 10.
total 10. 5 and 5, 6 and 4, whatever. Okay?
Why would they be opposite? Why should be 6 and why should be 4?
If they're at different angles. If they're at the same angle, then they're the same.
Oh.
That's all. Don't worry, we're not going to get too much into different angle ones. We've got a long time to go. Don't even look at the clock. Okay, so The sum of the two tension vectors must support the downward acting 10 newtons weight. The sum of the vectors must be 10, directed vertically upward as shown by the diagonal of the parallelogram formed by the two vectors. For an angle 60 degrees to vertical or 120 between the scales, 10 newtons of tension force is required in each scale. For angles greater than 60, the scale readings would increase even more. So this one here, I've gone to like really, really, really wide. It's 75.5 degrees in here, 160 degrees. Now I have 20 and 20. Well, because that angle is so much, my T1y still has to equal 5, right? This T1y is 5, this T1y is 5. But because the angle is so much, that means that my hypotenuse down here, my 20, has to be even more than it was before the 10. The wider I get, the
Harder.
more and more tension there is. Let me show you actual, like real life. There could be a Y component that could almost be zero.
Okay.
The only way it's
Okay. So in this case here, this is for the people that are listening at home. They missed out on that fabulous demonstration there. Where that thing blew up and it was really amazing, that I can't do again because it cost way too much money that they missed. Can't do that again. That really exciting thing, Johnny, that we just did?
It was pretty awesome.
Oh, yeah.
Yeah. It was so fun.
Can you see the people who watch this?
No, I can't see.
So you have no idea if people.
No idea. I can see how many people I can see views, I guess, yeah.
What's your average?
0.
Don't worry, I watched.
Thanks,
I
definitely.
usually watch them recordings after.
Okay. Notice that on the right, the angle from the vertical is increased to 75.5. At this angle, each spring must pull with 20 newtons to produce the 10 newtons vertically upward result. As the angle between the scales increases, the tension in the scales must increase for the resultant to remain 10. In terms of the parallelogram, as the scale's angle from the vertical increases, the magnitude of the tension force must also increase for the diagonal to remain that 10. If you understand this, you understand why a vertical clothesline can support your weight. So here's a kid hanging on a rope, no problem, but a horizontal clothesline cannot. The tension in the nearly horizontal clothesline is much greater than the tension in the vertical clothesline, and therefore it breaks.
So what about that guy who walked across like Niagara Falls?
There has to be a dip to the wire. There has to be. There absolutely has
They
to be.
feel themselves kind of
Here,
like.
EJ, you got one.
Going downhill? Yeah. They actually go downhill and they come uphill, yeah.
So it's impossible.
So if it's
Never
kind
done.
of.
Yeah, it's impossible to get it straight. Even if Ty and I grab an end each. Hang on a second. We're gonna. Ty, do you notice that the string is already
God, it's funny.
Okay. So, quickly here. If the children on those swings are of equal weight, which swing is more likely to break?
One with the bigger
Angle.
One with the angle, right? That kid's gonna bust that swing. Question number 2.
So scary.
It's a weird looking swing. Question number 2 says, consider what would happen if you suspended a 10 Newton object midway along a very tight horizontally stretched guitar string. Is it possible for the string to remain horizontal without a slight sag at the point of suspension?
No.
There has to be, as Ty pointed out, there has to be a dip because if there's a Y weight down, there has to be a Y force up. And the only way for there to be a Y force up is there has to be a Y component, which means there's an angle.
And it broke.
No. Even if it's like big, giant cable, right? There has to be it might be like unmeasurable, it's so small, there has to be some.
What if there's like a wind pushing it up?
Oh, well then now we're talking about a wind pushing it up.
And
Why don't we come from the ball?
An upwind.
Like blow it up, like it could like.
here's the thing, back and back. Yeah, what's it that?
Okay, I don't think you guys have this handout yet, right?
No.
Okay. So that first handout there was more or less sort of the theory behind it. Let's do some math now.
Okay.
Okay? We're going to do the math part now.
Okay.
So you already know one example of force in 2 dimensions. When friction acts between 2 surfaces, you must take into account both the friction force that is parallel to the surface and the normal force perpendicular to it. So far, you have considered only motion along the surface. Now you will use your skill at adding vectors to analyze 2 situations in which the forces on an object are at angles other than 90 degrees. So equilibrium and the equilibrant. There's a new word for you. Equilibrant. An object is in equilibrium when the net force on it is 0. That's key. I don't know if you need to highlight it, but I mean, it's certainly key. Right?
High key.
When in equilibrium, an object is motionless or moves with constant velocity. According to Newton's laws, the object will not be accelerated because there is no net force on it. You've already added two force vectors to find that the net force is 0. Equilibrium also occurs when the resultant of 3 or more forces equals a net force of 0. Figure 1a shows 3 forces exerted on a point object. What is the sum of A, B, and C, or what is the net force on the object? Remember that vectors may be moved if you don't change their direction. So, if I take vector A in red, and vector B in black, and vector C in blue, and how do we add vectors? We place them tip to tail. So there's A, and there's B, and there's C. Where do I end up? Back where I started. In other words, the net force is 0. Right? Figure 1b shows the addition of 3 forces A, B, and C. Note that the 3 vectors form a closed triangle. There is no net force, so the sum is 0. The object is said to be in equilibrium. Now suppose just 2 forces are exerted on an object and the sum is 0. So what if I've just got A and B? Well, then they are not going to be in equilibrium, right? In fact, the resultant is going to be, where would the resultant be of those two? Whoa, that was weird. Well, the resultant would be like that, right? Okay, now what does that kind of look like? It looks like if I do this, here's the resultant here. Can I do it in a different color? Okay, that was a bad idea. Let's just do it in green. Okay, so that's the resultant of those two, right? But that looks an awful lot like C, but in the opposite direction, isn't it?
Yes.
Okay. Suppose 2 forces are exerted on an object and the sum is not 0. How could you find a third force that when added to the other two would add up to 0? Such a force, one that produces equilibrium, is called the equilibrant. Key term. The equilibrant is the force that makes it equal. Go into equilibrium. In this case here, it's the green one.
Sounds like a movie.
The equilibrant. Sounds like a Dan Brown novel.
Equilibrium sounds like a month.
Yeah.
Yeah. Let's make it. I'll be the main character.
How do you find this equilibrium? To find the equilibrium, find the sum of the 2 forces on the object. This, of course, is called the resultant. The single force that will produce the same effect as 2 individual forces added together. The equilibrium is thus a force with a magnitude equal to the resultant, but in the opposite direction. So all you're doing is adding vectors, getting the resultant, and then flipping it. See how much I've set you up for this already? All you've done.
Almost like you planned it.
Almost like I planned it. Figure 2 illustrates this procedure for 2 vectors, but any number of vectors could be used. Okay? Now, some wise student, I don't remember who, I should have written down who it was, because they were pretty wise, said to me, Mr. Bennett, could we do this by vector subtraction? I'm like, yeah, you could. So let me just show you.
Okay, not just doing it.
Note that you can look at this as the vector example of vector subtraction. F net is 0, so you would write 0 is A plus B plus E, where E is the equilibrium. So the value of E would be 0 minus A minus B. It's vector subtraction. I'm like, cool. You don't need the 0. No, you don't. But it is a way of showing vector subtraction. Is that what you said? Good thinking. Okay, so now I've given you sort of the mathematical theory. We should probably do an actual example now, I think, right? Yeah, you have to leave? Okay, you go. So, here is an example. A 168 Newton sign is supported in a motionless position by 2 ropes that each make 22.5 degree angles with the horizontal. What is the tension in the ropes? There's a lot of tension in the room right now. No? Here we have our 168 Newton sign. What shall we put on the sign?
Yes.
I'm going to go with physics. The physics story.
No.
Yeah.
What kind of things can you buy?
Broken strings that can replace the one that Ty and I broke.
Yeah.
Go to Walmart.
Yeah.
Stuff like that.
Ah, Walmart.
Why do you like the fancy spring?
Oh yeah, fancy slinkies.
Just get it like slinky.
Anyways, I got two ropes that each make 22.5 degree angles with the horizontal. So that means that this is 22.5, and so is that. Okay? What is the tension in the rope? So let's call them T1 and T2. Is that okay?
What is the T set?
Tension.
Can you measure this?
Tension is measured in newtons.
Oh, but
It's just a force, right? It's a tension force.
Like, if you buy a rope, it's gonna have like this many newtons of.
It'll have rating. If you buy fishing line like I have here, right? It says 20 pounds test.
Why don't we use
So that means that this can withstand, on average, 20 pounds of force, which you'd have to convert to newtons.
Okay.
But it's how much it can. What's the rating on it, basically, right? Okay, so let's draw this. Let's draw the components. I'm going to go red for the component. So this is going to be T1y, and this is going to be T2y. This would be T1x. This would be T2x. What can you tell me about T1x and T2x? And opposite, right? Because this sign is not moving horizontally, nor is it moving vertically, right? But T1x and T2x are sort of acting opposite each other. Would you say that T1y plus T2y, oh no, I know how I got to do this to make it. Could you just say equals 168? Right, they have to be equal and opposite. T1y plus T2y is 168. Yeah? Are the tensions in the two ropes the same? Only if the angles are the same, so they are. So you could also say then that T2y is equivalent to T1y because they're both the same, right? T1, yeah, because this T2y is the same as like these guys. These y components are both the same.
So it's just that.
They're symmetrical, right? So in other words, I've got 2T1y is equal to 168, which really means T1y is 168 divided by 2, which is what we started off with way back when, right? Half and half. Each of the y components, Danielle, each of the y components, T1y and T2y, are equal to each other. So T2y can be replaced with T1y, and the two of them together, T1y plus T1y, well that's 2 T1y's. Now I simply divide by 2. So my T1y is actually going to be 84. Right? But that doesn't tell me what is the tension of the ropes. This only tells me T1y. So how am I going to get T1 out of T1y? Well, let's just redraw this triangle. And you don't have to do this every time, and I'm going to redraw it a bit bigger. This is going to be 84. This angle here is 22.5. This is the tension we're trying to find. What kind of triangle do I have? A right triangle. Sine, cosine, tan. So I got the angle. I got the opposite. Here I'm looking for the hypotenuse. So sine 22.5 is equal to the opposite, 84 over the hypotenuse, T1. Now, nobody likes it when the variable's on the bottom. We're going to swap those two, right? So T1 is going to be 84 over sine 22.5. Is it going to be bigger than 84?
No. Yeah.
No.
Way bigger. 219.5.
No. No.
Each of those ropes is going to have almost 220 newtons of force, which is what happened when I went really wide, right? It got more and more tension.
Where does it get that 200?
What do you mean?
If it's only weighing down 168.
It's because there has to be 84 up, but because the angle is so high, right? To get this to be 84, if this is 84 and this angle I guess is so small here, right? There's more and more tension here. Now you can use this if you're ever stuck in the ditch. Let me tell you a little trick. Hopefully it never happens to you, but if it does, you can say, Mr. Bennett taught me how to do this. Then you can phone me up and you can say, thanks, Mr. Bennett, here's a check for $100. Let's say you're in a ditch somewhere. Let me do it up here. Well, maybe $1,000. It depends on how much your car's worth. Let's say you're stuck in a ditch. No, I don't want to insert picture file.
How did you do that on calculator? 84 divided by 9.
84 divided by sine 22.5 equals. No? I'll come out of it. Let's say you're stuck in the ditch and you're trying to pull it out, but you can't. Okay? Here's what you do. If you're trying to pull something, this works for just about anything, right? If you're trying to pull it out, what you do is you tie the other end onto something like a tree or a fence post, something that's immobile, stationary. And then instead of pulling, you push right there. Because when you push right here, you create this kind of thing, right? And more tension in your rope, which means that it will, you're basically increasing your force by doing that.
Then you just put something really heavy on the rope.
So like
A car.
oh.
Right? Like there's a rope here between the desk and Sierra, right? Sierra, you're like the tree over there, right? So then I go like this, and I take this rope that is now tight between them, and I push here. And by the little push here, you get a lot more tension. Pull your car out.
That's cool.
It is cool.
But how does it pull your car out? Just by one person?
True, but you're only pushing, right? You're not pushing very hard.
I don't understand.
What if have you done it before?
I've never done this before. I stay out of the ditch. We could.
I really don't get it.
You should just do a lab and actually do it.
But what if there's no stationary objects?
Well, you gotta find some stationary.
I carry a
I don't think that would work.
Okay.
metal box in my
We'll
vehicle,
do
so.
that and then we'll.
How about you guys try this one right here? Oh, yes, you are, because all I've changed here is the angle. All I've changed
You don't,
is the angle.
so we're keeping it as one.
So it'll be a lesser.
You try this one.
Oh, does it just by the way, when we start we are T1 is equal to T2. The sine.
Yep. Let me go back and show the answer to this one here for the people watching at home, because I forgot to do it. They might have to pause.
It's T actually.
Are you supposed to what? Yeah?
Yeah.
Okay, well, let me get you started here. Oh, 8 Newton weight has one horizontal rope exerting a force of 6 newtons on it. What are the magnitude and direction of the resultant force of the weight? How do you find the resultant of these two forces?
A squared plus B squared equals C squared.
Can I do
You
that?
add them tip.
You add them tip to tail. How come I see people not looking, not good, then 10 minutes later going, I don't get this, I'm lost.
Just make it invisible.
But it's not football time to be talking.
But
No,
then
it's
you would
not.
have.
We just did it more than like.
We talk about the trajectory.
Whatever, man. 8 and 6. Can you do this? Well, of course you can. That's your resultant. Is it a right triangle? Yes. R squared is 8 squared plus 6 squared. 8 squared is 64. 6 squared is 36. 64 and 36 is 100. The square root of that is 10. It's a 3, 4, 5 triangle. For those of you that have taken carpentry class.
Right?
I don't like 3, 4, 5 triangles.
They're the right kind.
You didn't even laugh.
What's even
That was pretty funny, actually.
I look upset. How can you say you don't like 3, 4, 5 triangles?
What if 3, 4, 5?
I know, I understand that they're very simple. I understand that, but
You prefer the 3, 7, 14 triangles.
no.
They're not very square.
Because they're triangles.
when you say the triangle is square, it means it's 90 degrees. So if that's 10, now this is, whatever this angle here is, right? What force, magnitude, and direction is needed to put the weight into equilibrium? The exact opposite. This is E. E is going to be 10 newtons in the opposite direction.
Do we have to use
Yes.
direction?
E is equal to minus R.
Aha, okay.
There are no directions here, so we can't come up with anything. We would just say 10 newtons in the opposite direction.
Can we put negative 10?
You could put negative 10, I suppose, sure. Yeah. What are the magnitude and direction of the resultant force on the weight? What force is needed to put the weight into equilibrium? That's all I was asking.
I thought I was gonna have to find a degree.
Well, I mean, you should, but then you'd have to have a, I guess if this is south and this is east, then you could come up with an angle, right?
Yeah,
Right.
but it didn't really state it.
Doesn't state that. No. Johnny, pay attention, man.
Yeah, Johnny.
Okay. Now, try this one. It's exactly the same, except it's not right angles to each other. You're going to have to add by components. No, B was,
Okay, so A was finding R equals 10
Yeah.
and B was E.
yeah.
R equals
Okay, try number 3. Try it. Don't talk football. Don't talk something else. Try it. How do you add vectors? F1, F2. 60 degrees. F1, F1x, F1y. F2, F2x, F2y. How do you add vectors? You find the x components and the y components, and then you add them together. So do that. So we find the x component, we find the y component. We're going to do the same thing down here. I heard Danielle say they're the same numbers, just switch places. You haven't figured out yet in your years that cos 60 is the same as sine 30? No? Isn't that a trig identity?
What?
I think I know what that means.
So then you're going to add them together. So the resultant x is going to be that plus that. 84.7. Gee, I wonder if the other one's going to be the same.
Yeah, it is.
You're saying that 53 and 31 are going to be 83?
No, I'm not, but I just don't.
So the net force, the total net force, R squared is going to be, because it's the result. Remember we did adding vectors, you guys? Well, okay, so call it FR, tomato, it's the resultant force, right? Danielle, you're getting too hung up on labels again. Okay, it means the same thing. It's just, okay, then it's okay. You can be slightly wrong and still be right.
Nope.
You can be slightly different than mine and still be right.
You can be slightly wrong because
No, I'm freaking God.
you didn't get 100% from your driving test. Slightly wrong. Marley?
Didn't even respond. She's new.
119.8. Okay, now, it asks, we really do need a direction here, right?
So then you become an angle.
Well, What's the angle going to be if both sides are the same, the x and y? What angle is it going to be if this is 84.7 and that's 84.7? 45. You shouldn't even have to do the math. If you want to, you're going to get 84.
If the x and y are equal, then the angle.
Yeah? Does that make sense that it would be 45?
Do we need inverse
Yes,
10?
I'm clear.
Yeah, yeah. 45. So that would be 45 degrees above the horizontal. ATH. Above the horizontal. Because they gave this to me as both of these angles are above the horizontal, right? So 45 degrees. ATH for the second time. ATH standing for above the horizontal. So the equilibrium then would be 119.8, but not ATH, BTH, below the horizontal, and to the left, I guess, too, right? To be brutally frank, all I've done today is review how to add vectors and show you how to change the direction.
Yes.
Granted that they've been slightly different situations.
Oh man, that just took my brain for a spin.
Okay, I would like you to try number 4. This one says show using vector subtraction. I will come back to this on Monday. Try this for Monday. That's your homework. Try number 4 for Monday.